The maximum and minimum values of a function are called extreme values or extrema. And so this process is finding the optimization, or really the highest or lowest value of the function over an entire domain. So for the first few examples, we're just looking at the graph and we're trying to pinpoint where the absolute max and absolute min should be. And this is going to be very straightforward. Looking at your ordered pairs, keep in mind that the absolute max or min value will be the y values. That's what you're looking for, not the x. The x is going to give us the location, and the y values will give us the actual value of that function. So our absolute max for number 1 is going to occur at the ordered pair 4, 5. And notice this is at an end point. The absolute min, or the lowest point on that graph, is going to be here at the point 2, 1. And notice that is inside the interval. Okay, moving on to our next example. Now the absolute max, we're very tempted to say that the absolute max is way up here, but notice that's an open circle. So our absolute max here would be none. It's not going to exist because of the open circle. The absolute min is going to occur at the ordered pair -1, -1, and that is going to be at an endpoint. Okay, looking at the others, now this next one is a little tricky. Again, looking for an absolute max. Notice this function is unbounded. It doesn't stop at a particular place. So here our absolute max would be none because this does continue on up to positive infinity. The absolute minimum, again, it would be great if we could say it was right there, but it's not because of the open circle, so this one would be none as well. And then finally over here with our next one, notice that our max is going to occur way up here, so that's going to be at the ordered pair 3, 2, and that's inside the interval. And then the absolute min is going to be none because look at those endpoints there. So this would be none. So seeing all those examples, we run into a couple of definitions, and the first definition that we have will be a relative extrema, and that's going to be points on the graph where the function changes from increasing to decreasing, or vice versa. And if we look at some of the previous examples, especially for those that had some changes going on, we see that that's exactly where we had our relative extrema, or the absolute extrema. Absolute extrema is the absolute highest and lowest points on the graph of a function or a specific domain. Now, for us to have an absolute maximum or minimum, keep in mind that this part right here, this must occur over a closed interval. Now, for the previous, the relative extrema does not have to be on a closed interval, but absolute, for us to determine the absolute highest or lowest value on that graph, the graph has to be on a closed interval. So we need a for sure starting and stopping point. Okay, so notice in example 1, we're going to be asked a lot of times on the AP exam to analyze the graphs, and we need to be able to pick out coordinates of relative extrema on the graph. So notice for f of x, we're asked to find or approximate, and on the AP exam there would not be much approximation there. We would be able to for sure find it, but here we're going to approximate let's see, the coordinates of the relative extrema. So we're picking out both a relative min and a relative max for this. So looking at it, at our graph, a pretty good idea of a relative min or max. I'm going to read this from left to right. And notice our very first candidate should show up about right here in this area. And that's because my function is changing from decreasing to increasing. And so at that point right there, that should be a relative min. So I know over here for that very first one, my relative min is going to occur at, and it looks like that ordered pair would be negative 1.5, just kind of keep it simple, and at negative 6. Now you can have more than one relative min or max for sure. Now a tricky place to look at would be somewhere right here because we're almost tempted to pick something in that area. But if you notice, even though we flatten out here, that is not changing directions. Notice my graph is continuing to increase. However, this is going to be kind of foreshadowing the idea of a point of inflection. Now, we're not asked to find that yet. No, we don't know what it is, but I'm just showing y'all on the graph right now because we will eventually have to know. That is a point of inflection. My graph changed concavity. In other words, it changed from being opened downward to being opened upward. So that's going to be a point of inflection. We still did not change from increasing to decreasing like we did with the relative min. So looking on over a little more, notice we do have a for sure point right here. Our function continues to increase and then it gets to that particular place and then it changes and goes to decreasing. So notice that's going to be a relative max, and it's going to occur at the point 1.5, 1.5, comma 6. All right, so now let's talk about the next one. Is asking us to consider the domain of f where the absolute extrema. Now look at the endpoints. This is where if you're talking about absolute extrema, check out those endpoints. They're not closed circles. They're arrows to indicate that this function continues in the direction it's going. So we would have no absolute extrema, that's including both min and max, that's what extrema is going to do. No absolute extrema since the function is unbounded. In other words, it's not having a for sure starting and stopping point. Okay, let's go ahead and look at another example. Okay, now let's look at the graph of g of x. Now g of x wants us to state the relative extrema. And if we refer back to the definition of relative extrema for a moment, that's what we just wrote, we notice that that relative extrema is going to be inside an interval, and that interval doesn't have to be closed, but it's going to be where the graph changes from increasing to decreasing, or vice versa. So when looking at our graph, that's going to help us figure out, do we need to include our endpoints or not? And again, we're looking to see where our graph changes direction, increasing to decreasing and so forth. Well, that would automatically throw out our endpoints because there's no change there. We didn't change from increasing to decreasing or decreasing to increasing because it's an endpoint. There's nothing on the other side of those points for us to determine if that's happening. So we can determine here our graph goes from decreasing to increasing. So that's going to be a relative min there. And then notice over here at this particular point, I go from increasing to decreasing. So that's going to be a relative max. And then down here again, we go from decreasing back to increasing. So again, that's a relative min. And then up here at the top, we go from increasing, decreasing, relative max. So let's go ahead and put all of that we just found over on our answers. So our relative mins, that's going to occur at, and we had two places for that relative min. We had at -3, -3, and we also had that occur at 1, -5. And then we also had some relative maxes, and those would occur at -1, 1, and also at 3, 5. So notice all of those ended up being nice, neat relative mins or maxes there. Now, looking on down, we need to consider the domain. In other words, let's go over here and look. Do we have for sure starting and stopping points? And we do. So we can have an absolute extrema. And notice that that absolute extrema that we're going to pick from would be from our relative extrema, because the way that we have relative extrema defined is the place where the graph changes from increasing to decreasing or decreasing to increasing. So looking at those relative mins and maxes, we can pick out absolute min and max. So our absolute max, that's going to be the highest point that we see on that graph, is going to be 3, 5. And our absolute min, lowest point on the graph, that's going to be at 1, -5. Now looking at 1C, this is asking us to look at both of the previous functions and their domains, and we need to decide where extrema can occur. Is it going to be on the intervals or at endpoints? And then talk about our relative extrema. Now, this is where we can do a good example of the difference in an absolute extrema. So that's going to talk about both the absolute min and max. So if we talk about, I finished that A there, absolute extrema, that can occur at endpoints, because absolute is just talking about the highest or lowest value that's occurring on that function. And of course, this has to be closed interval. So we're going to talk about our endpoints. And then we also need to talk about that it can also be our relative extrema, one of the relative extremas. That's important for the absolute extrema. Now, notice that when we talk about our relative extrema, the relative extrema, now that can only occur inside of the interval. So make sure we see the difference there. This is going to occur inside the intervals. And those intervals do not have to be closed. Let's make ourselves a note. Can be open. In these examples, we're going to be looking at the same graphs that we just looked at, but we are going to restrict the domain. In other words, for this one, we're only going to consider the values between -2 and +2. So the rest of this we're not really going to care about. So again, right through here, this portion is the only part of the graph we're allowed to consider. So from here, we need to find the absolute extrema of this closed interval. So in other words, we need to find the highest value and the lowest value possible across this interval. And notice that if we do the absolute max, looks like it's going to occur between 1 and 2. It occurs, maybe let's go ahead and just say 1.5 and 6. And then the absolute min, that is going to occur at negative 1.5 and negative 6. Okay, now for the next part, now we're going to consider from negative 1 to 2. So we're going to change our interval again. So we're going to now look just from negative 1 to positive 2. So we've even shortened the interval even more. So we're just looking at this portion here. And now what are the absolute extrema? And so now we see that the absolute max is still going to be the same value here because we still had that point inside the given interval, but then our absolute min has changed. The absolute min is now going to occur at negative 1, negative 3. And again, that's because we've changed that interval. All right, so we're going to do the same thing for the next graph. We are going to restrict the domain, and that domain is going to be from negative 3. So we're looking from negative 3 all the way over to positive 3. And when we change that domain, that's going to change where our absolute max may occur. And notice if we're looking over just that interval, the absolute max is at 3, 5. And then the absolute min, that is going to occur at 1, negative 5. And then finally, if we change again and we make our interval from negative 5 all the way over here to positive 2, notice again values have changed. So now that absolute max is going to occur at negative 5, 4. And the absolute min will be at the point 1, negative 5. And so down here at the bottom, we've looked at several different scenarios for where our absolute extrema can occur. And so the first place that extrema can occur would be at the endpoints. And again, we're talking about absolute extrema, not relative. Be careful with this. We're looking at those places, so we can have at endpoints of an interval. The next place, and this is going to be kind of connecting our tangent line idea to our graphs here. So let's look at some of those graphs that we did earlier and notice that one place this could happen, especially in 1D where we had the rounded change of direction, that's going to be where we could draw a horizontal tangent line, and horizontal tangent lines have a slope of, and as soon as we say slope of, that's where our derivative comes in, a slope of 0. Or let's look at the graph that we have above. And this could be, again, where our tangent line has a slope of, and this one could be undefined because we have such a sharp point there, that tangent line could be vertical. And slopes of vertical lines, those slopes are undefined. So here we're going to have undefined. So now we're leading into the algebra side of things, of how we can find algebra to find relative and absolute maxes. And we're about to practice that. So the algebra side of this that I was just referring to is going to be finding a critical number. A critical number is found by finding the derivative and setting that derivative equal to 0 and solving, or where that derivative would be undefined. Now, if the derivative is equal to 0, that means we have a horizontal tangent, and then undefined means we have a vertical tangent. In other words, we have a sharp point there. The horizontal tangent means that we have a rounded change of direction, and undefined is a sharp change in direction. Now, our extreme value theorem, that is guaranteeing that if we are on a closed interval, then f of x has at least one absolute max and one absolute min. And that's all that extreme value theorem states. All right, so looking at our next set of examples, here it's just applying the extreme value theorem. So the big key part to that extreme value theorem is that the function is continuous over the closed interval. If the function is not continuous over the closed interval, then there's really not a whole lot we can do with that. So if we look at 2a, very quickly notice how our function is rational. And so we need to check that denominator against our given interval. And notice that if I plug in a positive 2, I would get to minus 2 in the denominator, which is going to give us 0. And we can't divide by 0. So here, that positive 2 that we're looking at is inside this interval. So our extreme value theorem does not apply here. And again, the reason why is because we're not continuous. And let's go ahead and write that in. F of x is not continuous on the given interval. And I know that, again, because if we take that denominator, set that equal to 0 and solve, we get 2. 2 is inside that given interval, so there is no way we're going to exist there. All right, so looking at the next example they give us, we're looking from -5 to 5. And notice that with what we're given, we are not taking the square root of anything. We're not dividing by anything. E to the x minus 2 plus 1 is a continuous function over all real numbers. So here we would say the extreme value theorem does apply. For g of x, because g of x is continuous on the given interval. Okay, and then our next example, again, we have a square root, and we know in the real number system we cannot take square roots of negatives. And so notice, to ensure that, what we would need to do is take x plus 2 and make sure that stays greater than or equal to 0. In other words, it stays positive. So I'm going to subtract 2 to see what set of x values I'm working with. And so x must stay greater than or equal to -2, but the given interval, this interval has values that are less than -2. You can consider -6, -5, -4, -3. All of those are smaller than -2. So for this example, our extreme value theorem does not apply. To h at x, because h at x is not continuous on the given interval. Now we're going to look at the algebraic side of what we just did on the graphs. So notice this is very important. We have what's called the candidates test. This is going to be is tested on the AP exam in several different places, so please follow what we're doing very carefully here. Now, for the first part, we need to find the extrema, absolute extrema of the function, and provide the EVT if provided the EVT is applicable, and if not, we need to justify why. So, in other words, we're going to go back to what we stated a few minutes ago in an earlier example. The first thing we're going to do is to find f prime at x, and we're going to set that equal to 0. So f prime at x would be 24x squared minus 6x minus 9, and I'm going to set that equal to 0. Now we're back to factoring. We're going to go all the way back to our Algebra 2 days. Now the first thing I can divide out of each term is a 3, so let's go ahead and reduce that. So I have 8x squared minus 2x minus 3 equals 0. And now let's go ahead and see, well, let's factor this. So a lot of y'all probably do the slide and divide where you multiply that 8 over. So you have x squared minus 2x minus 24 equals 0. And when we factor this, our factors that we multiply that give us 24 and subtract to get 2, and that 2 needs to be negative, so we're going to need a negative 6 and a positive 4. We do need to come back and divide by the 8, and then we can set each part equal to 0 and reduce. And if we do that, we have x is going to be equal to positive 6 over 8, which is going to be 3 over 4. And then the other side is going to be x equals negative 1/2. So our candidate test that we need to look at, that's going to be where we include both these values here and here. And we also, since we're talking about absolute, we have to also include our endpoints. So we're really going to set up a t-chart, and that t-chart is going to be hinged on f at x. So I'm going to have x, and then I'm going to have f at x, and really we're going to pick out the highest and smallest value after we plug in these x values. So the first x value that we're going to plug in would be negative 1. We also have positive 2 to plug in, and then we have 3 over 4 to substitute in, and negative 1/2. Now here y'all may use a calculator for this, because a lot of times if we're doing this type of problem, it is free response. It will be calculator a lot of times for these. And if we go through and start subbing back in, keep in mind we're plugging into the original f of x, not the derivative. We're plugging into the original function. Now when we go back and plug into that original, I've gone ahead and plugged in all of these ahead of time. And so for the first one, if I plugged in negative 1, I got 0, but do verify for sure to make sure. I plugged in the next one 2, and I got 36. I also plugged in 3/4, and when I plugged in 3/4, I got negative 3.063. And finally, when you plug in negative 1/2, you get 4.75. And now all that's left to do is pick out the smallest value under f of x and the biggest value under f of x. So the maximum value that occurs, now notice I'm just asking for the maximum value. That maximum value is 36. Now it occurs at 2, but I'm just asking for that value. And then the minimum value, which is going to be the smallest number I see in that lineup, so that's going to be negative 3.063. Continuing on with the next example, B, we're going to deal with trig, some of y'all's all-time favorite. So again, our very first step we do, we need to take g prime and set that equal to 0. So we're going to say 0 equals, and the derivative, we're going to have 1 minus 2 cosine x times the derivative of x, which is just 1. Now we need to solve this, so I'm going to subtract 1 over, and then I'll divide by negative 2. That's going to give me cosine x. And so notice that's really going to turn out to be a positive 1/2. We know cosine is positive in the first quadrant and in the fourth quadrant. And cosine of what angle gives me 1/2? That's going to be pi over 3. And so the next side is going to be 5 pi over 3. So there's our two of our candidates. And then here's the other two. So let's set up our t-chart. We have x, and then we have g of x. And we're talking about extrema, absolute extrema. So we include our endpoints. So we have 0 and we have 2 pi. And then we also have to talk about our critical points, pi over 3, and then 5 pi over 3. Okay, and again, I've gone ahead and typed these into the calculator, and so y'all are welcome to do so as well. And again, you are looking at these values on g of x. That's going to be our absolute extrema. Okay, so if I plug in 0, I get 0. If I plug in 2 pi, I got 6.283. If you plug in pi over 3, I have negative 0.685. And if I substitute in 5 pi over 3, I get 6.968. And now we talk about our maximum and minimum values. So our maximum value, in other words, the largest number that I see under g of x, is going to be 6.968, and that occurs at 5 pi over 3. And then the minimum value, or the smallest value I see for g of x, that is going to be negative 0.685. Now I'm going to stop the video here because it's getting rather lengthy. We'll pick up with the other 2, 3, 4 examples in class.